Hello, class. We're covering today a special class of integer programming models where the integer variable should just be binary, so 0 or 1. That's the definition of binary. So not just any whole number, 0, 1, 2, 3, 4. It has to be just 0 or 1. And there are numerous applications of this. The application we're going to look at, which is still an integer programming, but we have to add a constraint that those variables need to be binary, and that's bin, and I'll show you that in Solver. A good example is a financial example, which is capital budgeting. You may have covered different ways to do capital budgeting in the finance classes or accounting classes maybe. But here we're looking at the modeling, an analytics model that is different for capital budgeting. So what are we given? We are given certain number of projects to do we fund them, do we not fund them for next year? So the inputs would be the cost and the net present value for each project. The decision variables usually are which projects do we do? So we know very well that there is always more projects to do than there is money to do it, that there is budget to do it. And so, you don't want to upset everyone, but you also can divide the money among all the projects that are needed. So you really need to decide which projects to pick up for next year or not. And the objective usually, since you already did the work of the net present value, which is the value of each project, is how do I maximize from all the projects that we select, how do I maximize the total NPV value for all the projects? At the end of the day, we care about the organization as a whole. And the constraints are budget, maybe there is more constraints, order of projects, and then again, so what kind of model do we use? So let's jump. I think now you're pros with the template or the shell, and you know how to format it, you know how to set up the spreadsheet model. So we're going to go directly into the solution. And you have the detailed steps in your book as well. So if we're looking at the solution, this is the simplest, again, model there is. And so I'm going to show you the layout is very simple. We have 7 projects, or it could be investments. I'm looking at investments to make. And so each has a cost. I have to put my money in, and maybe there is a net present value. These numbers could be in millions, like it says here. So the cost for the first project is 5 million, and I did my calculations for NPV, and my return is 5.6 million. So I would make 600,000 on this project. That's my return. So as long as the net present value is always higher, then you're going to make money. It's just how much more money you're going to make. So here's the new thing in these type of problems that involve binary variables. My decision variables are simply, do I invest in one or not? If I invest in one, we want Solver to put 1 in this cell. If I don't invest in it, the optimal model doesn't invest in it, I put 0. The model puts 0. So each of these values are not fractions, and they're not whole numbers like the employee scheduling problem. They're either 0 or 1. So another constraint is the budget. I have 15 million. This adds to more than 15 million. So if I sum this row, I will see that I have, almost double. I have projects that will cost me 31 million, but I only have a budget for 15 million. So I have to pick and choose. And this is a simple model because, it could be 70 projects, 700 projects. I mean, a department will have more than 7 projects, but we're showing you the technique here. And so, okay, so that's a constraint. And my objective is always to maximize the total NPV from all the projects that get selected. I mean, because each of them has a different NPV value. And so total NPV is the sum product of the project, whether it's selected or not, with this range, the NPV. So again, the sum product comes to our rescue, so we don't have to repeat the formula multiple times. Okay, with 7 projects, you may be able to guess. I mean, without doing an optimal model, what would be a quick way of doing that? So if it is, for example, if you do an ROI, another metric you learned in finance, return on investment, just like you learned time value of money for the net present value, it's 12%. So you divide NPV divided by cost, and you subtract 1. So I'll make 12% on this project if I carry this project. I make 12.5%. I make 11.4%. And so there is a modeling heuristic, which heuristic is a near optimal solution. It's a good rule of thumb, but it may not give you the optimal solution, which is called greedy heuristic in modeling. And the greedy heuristic is, come and say, okay, well, it looks like project 6 gives me the highest return on investment, so let me do project 6. And so if I pick project 6, I'll see that I still have almost 10.5 million left. What's the next? Or actually, it is project 4 that is higher. And so then this is the next higher. So I can put them both in and then go to 12.5. I still have some money left, and then go to 12. I believe that's the largest. And I cannot do 1 because I exceed my budget by 8 million. So I have to pick something smaller that has a cost almost of, what do I have left, 2.2? Well, nothing is 2.2. This is 2.4. So these are the 3 projects, and it's total NPV of 14.6, and I have some budget left over. So you can guess more. So this is 1, 2, 4, 6. If we come here on the side and write greedy heuristic, recommends 2 projects, 2, 4, and 6, 2, 4, and 6, and total NPV is 14.6, and I have money left over, unfortunately, that in some organization it's use it or lose it, and so you cannot really use it next year, so it's gone. So anyway, let's see how this works with the optimal solution with Solver. We go home, data, Solver, and setting it up this is our objective function, total NPV. We want to maximize it. The decisions are these pink cells, and we want total cost to be less than budget. That's clear, less than or equal. But this decision binary is similar to what we did in the constraint. So if we're adding a constraint that's binary, I'm highlighting these, and I am clicking down on bin, which stands for binary. So there is no way around it, like with network models for integer constraints. binary constraints, you have to include that. So total cost is less than or equal to budget. Simplex LP, still it's LP. The variables have to be 0 or 1. And unconstrained, non-negative constraints. Solve. And interesting because, wow, now it picked 3, 5, and 6. The optimal solution is 3, 5, and 6. I make more NPV, so this is the optimal solution. And the better thing is I use all my budget except for $100,000. And so this is project 3, 5, and 6. And I make 1.7 million, almost more than 2 million in extra total NPV, which is a good thing. And so that's really, really powerful if we have 70 projects or 700 projects throughout the organization, and we want to do the ones that really give us the most bang for our buck. And so ROI is the most used, and even that gave us a suboptimal solution with 7 projects. There is an extension, of course, with sensitivity analysis. You can increase the budget and see what more projects can you do, but we've already done enough of the solver table. I want to show you an extension, which is interesting. If we have 2-year costs, not every project is done in a year. So we have 2-year costs, and we have 2-year budgets. And it's exactly the same thing, except your ranges have increased. And so if I'm doing the, total cost of year 1, it'll be these decision variables, cross-multiply them by the year 1 cost. Year 2, these decision variables, multiply by the year 2 cost. And then, interestingly, because of the way I can set up solver, none of this changes. Now the total cost is less than the budget is these 2 cells, less than these 2 cells. And the rest is exactly the same. And you solve, and now it tells you which project you can complete. Basically, you don't want to start a project if you cannot support it with year 1 fund and year 2 funds. And so that's the limitation here. Now, there is an extension of this extension, which is maybe if I have leftover money from year 1, I can roll it to year 2. And that's also an extension. And that's a useful one, because with some organizations, you can roll over the money. So this shows you a great example in finance, but there are capital budgeting projects in operations and supply chain, in IT. Any organization will have the dilemma of what to invest in, what to not invest in, and hold back for next year or next 2 years. And this is capital budgeting. Thank you.